can go to cores, isn't it?
Yep.
And what we wanted was the 0.922, wasn't it? So let me see. Not op param, sorry. This dot, isn't it?
Oh yeah, this stuff.
So this opt. And now core 0.922, wasn't it?
Yep.
And let's just do it like this. The index rate, and now start the stream. See, much better.
Oh.
You see? So about 7% better. Even though there are fewer images. The fewer images is because it takes much longer to finish this. At some point it just gets himself killed. That's why it doesn't finish at those at that. You know, after, if it takes, I think the day run takes at most 6 hours. If it takes more than 6 hours, it just cuts it. So that's why. But I mean, it doesn't matter. We can see clearly that this one is producing a lot more, so a lot more indexing than your distance optimization. So no, the question, of course, is we can take a look like this. See here, your threshold is 2,800.
Oh, you mean the first?
Exactly. So this is the one for the distance optimization. You see.
Oh.
So it was the threshold was at 2,800. However, also do notice, oh no, your minpix count is at 1. So yeah. So it looks like the 2,000. So we can take a look at the comparison here. Okay. And let me just go real quick. More. I know. See param. Okay. And now more this guy. Okay. So we can see the initial command. So it's there. Okay. See. So we can copy this, since we can do it like this. So what I suggest is that you have here a editor notepad, okay, and we take this and we copy it and paste it. There you have it. So this is the original one. So this is the one that it's finished right now, and now we can do exactly. We can compare it to see what is the difference. Okay. So we can go to this one, and we need to go one above. Okay. And now we can take this one. So let's take this, and then we can paste it here. And so, see, the main difference that we have is so CX on the flat cell. So try multi, check peaks. Okay. So let's see. See, integration radius. It's 356. Same thing. Okay. Then sorry, tolerance is the same thing. Retry multi, check peaks, minpix count. You have minpix count of 1. Where is minpix count of 1? Minpix count of 1. Local background count, so local background radius 4. Xcount of sample pitch 6. Xcount of grad desk iterations 4. So you see, it's the same thing.
Short hold is only
the only difference is the threshold.
Yeah.
Okay. So that means that clearly lowering the threshold is providing an improvement. What do I suggest that you do now? Well, if lowering the threshold provides an improvement, your next step should be lowering the threshold even more. Because we've seen it improves it already.
Yep.
Maybe the other ones will improve it. Maybe we find some region in the middle that makes it even better. You see? But since we're now more or less waiting, what we can do is just go nano opt sh, okay, and what we can do is go down here, and we know that 2000 was good, so was providing more indexing, isn't it?
Yes.
So that means that let's go down here and let's say, for example, 1600, 1200, let's do 800 to 1600.
Oh.
Okay, so then we will try 800, 1200, 1600, and 2000 is already there, isn't it?
Oh.
So we save it. Okay, and now history grep minus is batch. So we just run it as this one, isn't it? And the other thing that I want to check so that we get a full run, okay, is where is it?
Not this one.
Okay, it was somewhere at the bottom, somewhere here, minus t. See, see, the day is supposed to be 4 hours. So if it lasts more than 4 hours, it will just stop the run. But we can give it a maximum of 24 hours. So since this one was at 9,700 after 4 hours, probably giving it 6 hours should be enough, isn't it?
Yeah.
So that means that what we can do is, right, so we can copy this one. Hey, where is it? Here. And then we provide also minus t, so for time limit, 6, and so we provide 6, 0, 0, 0, 0. Okay, so that means 6 hours. Okay? Hours, minutes, seconds. Okay, and so we run it, and we should now have a new Slurm file. See, now we have a new Slurm file. Okay, and now we can check the Slurm file to check that we do have. See, it's run 3 more jobs.
So Slurm file is the job.
The Slurm file is the log file for the job submitting system. So what you're doing here is basically this is a front end to the supercomputer, and this SBatch sends files or sends jobs to the supercomputer. Okay, and so the point is that the supercomputer has a scheduling system, meaning so that we don't overrun it with jobs and so on. And that scheduling system is called Slurm, for whatever the reason. So SBatch is the interactive mode to send files to Slurm. So it will just submit jobs, and so it produces a slurm.out file every time you run an SBatch job. It produces a slurm.out file where you have all the stuff that Slurm is telling you about what it's doing. You see? So, by the way, why do you have several of them? Let me just check this. More. This one. Yeah, that's because it. So, and again, whenever it starts running one file, it will produce this an extra one where it says, so it gives you the information of what's running. Okay, so whenever it actually starts running the job. Okay, so, and of course we can still see what's going on. Okay, see with the other ones if we see some important difference. So you can see that right now we don't see much of a difference between them, isn't it? So, I mean, what we're seeing definitely is that at the beginning we have a lower hit rate than at the end. Okay, but that's fine. So that's not a problem. We just need. What that means is that we need to wait until the end to decide which one is better.
Oh yeah.
See what I mean? Because if not, right now, what does it mean that at 2,600 images, 2,400 has 41, while at 9,712 images, 2,000 has 57? You don't know.
Yeah,
maybe, exactly, maybe as it continues to run, these guys will become better. You don't know. Okay, so that's why you need to wait until it's done. I mean, what we can check, because you should have it here, this one here might be able to tell you about that.
Log file?
Yeah, that log file is the output from the IndexaMagick file. So the IndexaMagick job, so the actual indexing job. Okay, so it's designed like that. If you look at the script, you will see that it's the output of the IndexaMagick file is supposed to be written in here. And so if we open it, okay, see, this is telling us, the different files and whatnot, and all the different stuff that is running. Okay, and as we continue here, blah 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 blah, see, we can see, so you can see here it's telling you, okay, it's looked into 1900 images, and those provides 32.9% indexing rate. You see, so we were looking at 2500 or something like that, so we can look here, see, there we are. So if we look at 2500 or so up here, we see that this was giving a 34% indexing rate. You see, so if we compare it, index rate star.stream, see, this is 2564. Okay, so if you see here, for example, 2800 is providing right now about a 42% indexing rate. So you can see we can expect
Can get higher?
that 2800 will be better than 2000.
Oh, yeah.
You see what I mean? Because at about the same value, we have a much lower indexing rate for 2000 than for 2800. That could be something to do because we have some extra commands in there.
Oh, yeah.
Okay, so if we look at it here, see, so see, we have here retry, multi, check peaks, but here, see, we had you had here minpix count 1 and 2, so it's probably choosing this guy here, so it has lower, so it has a minpix count of 2. You see what I mean? So, and the minimum resolution and max resolution are different as well. You see what I mean? So there you have some differences. I don't know why it's here twice, but normally it will take the last one. So this one here, okay? And the other thing that should be different here, if I remember correctly. So that could be a big difference, okay? And I think that's it, isn't it? So that's the big difference there. Okay? You see?
But is crockery cell different?
Sorry, what?
This one and this one?
They should be about the same, especially because you have the range in there. So, but you can see that that's the big difference. I think that here it's truly minpix count equals 1. Here it's probably minpix count equals 2. Okay, so and that's giving you a bit of extra images. And of course, the other thing we can do is to take a look at how the unit
this
cell
one
looks.
behave with this one.
Exactly. And you can see it looks really beautiful. So we can try and see, we can open it up a bit, and I mean, it looks very well optimized. Okay, so we have a very nice overview of the, and so if we go like this, and like this, and like this, like this, like this, this, we check. So what was the unit cell that you had calculated initially?
Here.
Yeah, that one, the first one. So you had 50.82, so here we have 50.83, 65.65, that's the same, and 153.1, and here you have 153.08. So basically the same unit cell. Okay. And yeah, so that looks very nice, I would say. So yeah, so that means, and notice that now, of course, the distribution, we don't expect much change, isn't it? So the distribution should be the same because we're not changing the detector distance. That's why we're now looking only at the indexing rate.
Oh, okay.
You see, because that's where we expect changes to occur or changes to be important. Okay, so we can continue to check. And so basically that's what you have to do now.
So
and
try
see-
to find out the a parameter that has the highest integration.
Exactly. Okay.
Change all the things.
Yeah, and see 800 has started.
800.
See threshold 800.
Oh.
So now you have it there as well. Okay. And so hopefully this will run until at some point it will finish. And it will give us some value of the so it will give us sort of a good optimization for the threshold. Okay, so once you know the threshold, what do? You go to opt
Two.
2, okay, and here you provide the right threshold here.
Oh yeah.
Okay, you give the right threshold there.
And do the mean.
Exactly, and then you cover Mimpix count. Remember to
Yeah.
do so. You cover it like this, okay,
And do it from
and
1 to 5.
from 1 to 5, and then it will start to run it from 1 to 5, okay, and then yeah, and when that and also remember one thing: when you have two values that are very very similar to each other, I suggest that you don't wait, just submit the two jobs. So for example, I'm fairly certain that by the time you're at 9,000 with all of these,
Yeah.
you will see a clear difference between them. Okay? And so let's say, for example, that 2,800 produces a 58% or a 59% indexing rate. Meanwhile, 2,400 produces a 58% indexing rate. Now, in 1,000, move around by plus minus 0.5%, it's possible.
Yes.
So instead of waiting for another half hour or 45 minutes to see which one is the best one, just run opt 1 twice. One with 2,800, one with 2,400.
Oh.
You know what I mean? Don't wait for this one to be finished. If not, you can wait forever. Okay? And then we have a better overview of what happens when you mix different sets of parameters. Okay? And so with this, you should be able to fairly quickly get your optimized parameters. However, if you ask me, my guess is that you're not gonna get a significantly different set of values. So that basically what you're gonna get is the same that we got for what's it called for MMCPD2. I mean, maybe you find some differences, but
And then,
but
but I still need to find it.
yes, because in theory it could depend on the crystal. The point is that the unit cell of both crystals is quite similar. So if we look at it more, the crockery cell, okay, so this is the crockery cell, and if we go back here,
One more.
uh, 23 opt param. See, if you look at the two unit cells, they're fairly similar. Okay? What I mean with fairly similar is that the spots are going to be at similar distances.
What? Why?
What do you mean, why?
Because they're not the same.
Well, they're not the same, but they're they're fairly similar. You have 65, 110, sorry, 65, 72, and 153 and 169. So I mean, in 2 out of the 3 axes, namely the longer ones, you have very similar values. Which means that for the purpose of being able to separate the spots, you're gonna need similar parameters. So if we would be looking, for example, at MMCPD2 crystals just by themselves, okay? So no DNA, just MMCPD2. The C-axis is 256 angstroms. Much longer, which means that the spots are much closer to each other. So the spot finding algorithm is going to need quite different parameters to be able to tell the difference between the spots compared to these guys. But because these unit cells are, similar enough, okay, the spot finding algorithm is going to need similar parameters. You have to think that means, so 50 and 65 is pretty similar to each other, and both of them are fairly similar to 72. That means that overall you're going to have one axis in this case, okay, or two axes in this case, one axis here, there is going to behave fairly similar to each other. And the other two, 153 is quite similar to the C-axis, so the kind of parameters that you need to tell the differences in spots here are pretty similar to the ones up top. So that means that you don't expect to see a huge difference in behavior. The only thing is the size of the peak. That could make a difference. So meaning the size of the peak, so how broad is the peak, that has to do with the intensity of the diffraction. So meaning you can imagine if you have the same, let's imagine that it has the same decay in both cases. Okay? So if you have the same decay in both cases, that means that the shape of the Gaussian, of the 3D Gaussian, which represents each reflection, is going to be the same. However, let's imagine that now you have a crystal that has twice the volume. If it has twice the volume, you expect to get twice the intensity in the peak. But if it has twice the intensity in the peak, that means that the decay, because it's twice as high, since the decay has the same form, it's going to be broader. You see what I mean? So, because if not, the decay would be different, isn't it? So if the decay is an exponential, if you started twice the height, so let's imagine if you start here, the exponential is going to look like this. If you start here, the exponential is going to look like this, isn't it? It's going to move to about twice the distance on the x-axis. So that means that given the same shape, if the crystals are somewhat larger, the spots are going to have higher intensities, and if they have higher intensities, that also means that they're going to be broader peaks. They're going to occupy more pixels, isn't it? And so if that is the case, what does that mean? Well, that means that maybe min-pix count you need to raise it to 2, or maybe the spot radius you need to make it a bit larger. You see what I mean? That could make a difference. But even with that, I think that the shape of the crystals is fairly similar to each other. I mean, these guys are rod shaped. The MMCPD2 are little cubes, isn't it? But I'm talking regarding the amount of light that passes through them, the what's called the path length for the X-ray. I think it's fairly similar to each other. So about between 20 and 50 micrometers, something like that. So that means that given that, the intensity should also be fairly similar, and therefore I don't expect either that the what's called the spot finding algorithm will need a difference in the min-pix count, so how large that area becomes. Yeah. So yeah, that's it. And so overall, I think it's looking fairly good. So. And yeah, so we can see that these guys are going up. Yeah. So hopefully, when this is done, you can run it. Now another thing you can do, what was it? SQ, wasn't it? SQ. Was it by user? Do you see it there? By user. Yeah, by user. Let me just check real quick. Yeah, xmaestre _n. So you can do SQ minus U x minus maestre _. underscore M,
Mm-hmm.
and then it only shows you the stuff that is running right now. Okay, so now my suggestion to you, okay, is that the jobs that are currently, so the jobs with low with low threshold are not going to produce very good data. Okay? Simply because we just saw it for the same value, the one with 2000 was producing worse indexing than the ones with higher threshold.
Go upper?
Not necessarily, just let it run, okay? Because we don't know. Okay? But my point is that if you see the old jobs finishing, what you can do is you can delete the new jobs. Okay? How do you delete them? Oh, no, this one. Where is it? This one. So let's see. SQ.
The old one?
So what was the command? Was it qdel? I think it was qdel. No. Let me check again. Slurm delete job. S cancel. Exactly. So you can do S cancel. Okay, and see. Where is it? Exactly, S cancel and then job ID. So you can do S cancel, okay? And so you can see here, this is the minutes that the job has been running, okay? And so you can see that these jobs here have been running for about 45 minutes, you see?
Yeah.
Meanwhile, these jobs here have been running, one for 13 minutes, the other one for 7 minutes, and this one for 0 minutes, you see? So that means those are the new jobs. These ones are the old jobs, isn't it?
Yes.
So, how do you delete the new jobs? Well, this here is a job ID. So you just take the job ID and you write S cancel followed by the job ID. If you press enter, it will kill it.
Oh.
Okay, and in that way you free up space in the queue to submit new jobs.
Oh.
Because if not, they're gonna, at some point, like this one, because you have other jobs running, this one is waiting to finish. If at some point you have like 10 or 15 optimization jobs running, maybe some of them you're fairly certain that they don't work.
Oh, I see.
Do you know what I mean? So now another thing you need to think about, this is important in that sense, is that there are jobs, okay, in there. So basically, because we have this retry setup, so you remember here, so here, see, retry, okay? So that means that if it cannot index the image, it will try again. And if it cannot do it, it will try again. So that means that when indexing is good, the job will be fast. When indexing is bad, it will try again and again and again and again and again, and the indexing will be, and the job will take a long time. So especially when you're working, for example, the signal to noise ratio, when you go down with the signal to noise ratio to say 2 or 3, there are a lot of extra spots that appear, isn't it? So that used to be no signal, but because you lower the signal to noise ratio, all of a sudden they become spots. And so now all of a sudden, images that were easy to index before, when you lower the signal to noise ratio, they become very difficult to index. Okay? So what happens then? Sorry. What happens then? Well, what happens then is that you have, so that the job will take a very, very long time, and you will see that for low signal to noise ratio values, it will take maybe 2 or 3 times longer there than for high signal to noise ratio values. So what that means is that at some point you will clearly notice that the low signal to noise is not producing extra indexing. Right? And at that point you should just kill that job and continue for the next one. Do you know what I mean? So, and you can use the trick that I just showed you, where you look into the log file of one that is finished, you look, let's say after 4,000 images in the low signal to noise ratio, you check at the same level for that, and you see, oh yeah, this is producing only half of the indexing, so meaning that's probably that's not going to produce good indexing at all. So let's just kill it and go for the next step. Okay. So that's that one, and so we can take a look again. See, for example, well, actually no, because probably that one. Well, we can take a look real quick in a moment. Yeah, so these ones are not producing much of a difference there. But yeah, so yeah, so there we have it. Okay, so I mean, for example, right now, 3,200 looks very, very good. Okay, so maybe even higher. We'll have to see. Yeah, as it finishes, we'll have to see.
So how accurate is the shear-hold need to be into how much between the shear-hold digit?
Well, I'm using 400 because I know that the actual threshold of the system is at about 2,000. So this has to do with how the detector counts electrons. Because the threshold is actually a value that corresponds to the number of electrons that is detected per pixel. Okay? So in SACLA, it's counted in hundreds. So in SACLA, you're going to be somewhere between 0 and 1,000, more or less. Okay? In Swissville, it's counted in thousands. So in Swissville, you're going to be somewhere between 2 and 4,000. So between 2,000 and 4,000 in most cases. Okay? So that depends on the device you're working with. Okay? So in this case, that's why you can see it's about the 2,000 something. If you want to check it, okay, sort of what's the detector, what we can do is we can do Christwell. Okay. Come on. Okay, and now we can load data. Problem is that, as you can see, this takes forever. And then we load a stream file. And to load a stream file, we take one of these. Okay, so param, and we take the one that was finished, which was 2,000, wasn't it?
Yep.
So where is 2,000? Here. Okay, so we select this one and import. So this is the image, okay, and if I remember correctly, how did you do this here? No. Show results from here, exactly. And next image. Let's see. The problem is, as you can see, it takes forever. This you could do locally, but if you do it like this remotely, it's like it takes millions of years. Come on. Are you connected by cable or by Wi-Fi?
By Wi-Fi. Still by Wi-Fi.
That's why so you should definitely connect by cable. Yeah, this we cannot do here at this point. This is not gonna work. So basically on this image you can actually check the numerical values of each pixel. Okay, and so by checking the numerical values of each pixel, you can actually tell. You look into the areas where there is no data, and it can tell you more or less what the noise is, and the noise should be your threshold. See what I mean? So like what you want is that if it says there that the background is normally being counted in like values of about 2000 or so, then that should be your minimum value for the threshold, and from there up. See what I mean? So can we close this? Ah, there we are. Finally. Okay, so let's see if there is anything. Of course. Okay, whatever. We can let it sit for a while. Let's see, we have the images there, and view. You can see how long it takes. This is the problem. Come on. Okay, whatever. I don't care. Let's kill it. But yeah, basically you can open it like that, and that will show you sort of the background at that point. So how much is in the background. And again, we can continue to take a look at it. And see, for example, we can take a look at this one. So you can see 3,600.
Yeah.
We're at 54% for 7,211. Okay, so we can take a look here and see and compare. Okay, so at 7,200. Hey, yeah, sorry, at 2,000. I took the 1,200.
Oh.
See, there we are. So this is giving us about 43%. Okay, so let's continue to check here to see when it reaches the final point, because that's, I don't understand how it's producing this set of values here. That's why I don't understand how. Ah, yes, because it's doing it with the two jobs. Yes, because it's showing you only one of them. See? Yeah. Where is it? Opt. SH. Hey. When you do here, you see it's running down here. It's running Diracs and X Gandalf. It's running two types of jobs. You see, the indexing, it's using Diracs and X Gandalf. Huh? So, and here it's only showing you one of the jobs, not both. So the results from one of the jobs, not from both jobs. And so that's why it's giving you that. So that's why you cannot see it. So that means we cannot really say much about it. But if you want to show you what I mean, I'll show you what I mean. So, come on. So, okay. See up here? There's Diracs and X Gandalf. Yeah? So if I disconnect this, see, I am only left with 823 out of the 5,596 that it could index. So that means that Xgandalf was able to index 5,500. Was able to index 5,596 minus 823. If I go to the opposite one, see, I connect this one. See, when I disconnect Diracs, I am left with 4,773. Why? Because what we're telling it is to first try to index using Xgandalf, and then if Xgandalf fails, to index with Diracs. Yeah? So, which are two different ways of indexing. Again, if you want to read about it, go up and you can check what Xgandalf and Diracs does. I use both of them. Basically, Xgandalf is a bit slower, but it's very good at getting double conformations. Do you know what I mean? So if you have two of them like this, two crystals, one overlapped over the other, Xgandalf can separate them very well. And Diracs is super fast and always gets a bit extra. So I let Xgandalf run first, and then I do a second pass with Diracs to sort of really get everything that I can that Xgandalf couldn't. Yeah? And so that's why we have those two. And but yeah, so if we check, for example, with Xgandalf, we have 4,773, which, as you can see, is about that one. You see? It's about this one. You see? The indexable ones. So that means that here it's only reporting the Xgandalf values. We can, I mean, if we have this issue, what we can do is simply compare the log files. Okay? So we can do this.
Oh, you mean compare log file to log file?
Exactly. So here we have 2,000. Sorry, let's do it the opposite way around. Let's take 3,600, for example. Okay? So we can do the comparison. 3,600. Okay? And we go to the very bottom, because the indexing will be proportional, isn't it? So actually we can do it much more easily than this. And so we can do like this. Well, tail. So you can use tail instead of more. Use tail, and it gives you the last one. And you can see at 3,600, it's at 42%, 45% for 7,700 hits. Okay. Now, what we can do is, so now we can go for 7,700 hits, and we check here. Okay. And we just continue to go like this, because now, of course, we need to find something that is similar. See, about here, and so we see that there's about a 1.5% difference, which is a pretty significant one. If you think about it, over was it over 7,000 images? The 1.5%, that's 1.5 images for every 100. So that means that that's about 100 more images, isn't it? Because it's 77 times 1.5.
Yeah.
So you see that's a significant difference right there. Okay, we can take a look at the other one, so that 2,800, to see if there is a bump in the middle already, isn't it? So, but actually, let's go the opposite way around. We can go tail, because this one we need to look at it. This one is not as far, isn't it? See, this one we're at 4,818 with 39.1. Okay, so at about 5,000 images. Okay, so, and we can look here at about 4,800 images, 5,000. here we are. And see.
Around here.
Yeah, exactly. Around here, we're 38.6, which again, it's about 0.7%, something like that. So it looks like it's sort of becoming better and then going down. You see? So, I mean, it looks like it's becoming better. Whether it's becoming better like this or becoming better like this, we don't know yet. Or we can check in the case of 3,600. Okay, 3,600. Okay, and then we can take a look here, going to about 4,800, isn't it?
Oh.
See, now here we do see a good increase. See, 39.7, which means that it is about a 1 point something percent above above the 2000, but also about a 0.5% above the 2,800. You see?
Yeah.
So that means that it looks like 3,600 is looking better. We can check, for example, what happens in 3,200. See if that one becomes even better or worse, or where it is sitting there. Okay, so we can go like this. The other thing is that also you have to think that those 300 is probably images that it could actually index, because it can't understand the unit cell. That's a bug on the system. Actually, when you do the full indexing, that bug is not there, so it will work properly. So you will get even more images for the full indexing. Okay? So, but if we go here and we look at see, this one is even better. It's about 40%. Okay, so that means that, well, now we can see that it's going to be somewhere there. 3,200 appears to be the best one. Now, if this is what you get, then one option that you have is to do 3,000, and what is it? And so this one is
3,200.
It is 3,200, and you have 3,600. So why not do 3,000 and 3,400?
And how detailed do I need to?
I mean, I don't know. That's up to you. So I mean, but we can run that actually. So I mean, now that we see this, we can be fairly certain that those guys, so the new jobs, we don't need them, isn't it?
Yeah, I can just kill.
So we can do SQ minus U to check the names. Okay. Okay. And now we do S cancel, and we take the oldest files, which you can see as batch. These are the new files, you see, and these are the older. So these are the old files and these are the new files. Okay, so we can do see, it's from 93 to 35. Yeah, as it's 1, 9, 8, 9, 3, 4, and 5. You see, so we do like this. And now we should see that those files are gone. So now we can go to nano-opt.sh, and now here what we do is, instead of from 800 to 1600, we can set it from 3000, okay, to 3400. Okay, so it's only going to be 2 jobs. Okay,
only 2 jobs?
Yeah, because then you're between, remember we had 2800, 3200, and 3600, and we saw that 2800 and 3600 were worse than 3200. Therefore, let's try below 3200 and above 3200.
Oh, okay.
You see what I mean?
So we need to change this one?
No, 3000 to 3400 is in steps of 400. That's going to give you 2 jobs, isn't it? So now we can run sbatch. Here we are. S batch, this one. And we run it. Hey. Oh yeah, exactly. And now we should be able to take a look here and see that there should be, okay, let's go. See, we should have now exactly 2 jobs that are running right now. And now we should be able to like this. And see, of course, these 2 are broken. So 1,600 and 1,200, they're not going to continue, isn't it? But here now we have 3,000 and we have 3,400, which are the 2 ones that we were the 2 that we were interested in, isn't it? And you can see that 3,600 now is at 57.4 at 8,568. So you see, it's gonna probably end up at a similar value than 2,000. Okay. Maybe a bit higher, isn't it? So, okay. And you can see how raising the threshold makes things faster. Notice how the 3,600 is running like crazy. It's much faster than the other ones. If we check, okay, CDS badge here, where is it here? Sorry. They've all been running for about the same amount of time. About 1 hour and 10 minutes, isn't it? However, 3,600 is almost twice as much, is about 2,000, about 3,000 faster. Has processed 3,000 more images than the other ones, even though it's running at about it started at about the same time. Why? Because the threshold is higher, so many spots disappear, and therefore it's easier to index. Now, if you get the same value, the same indexing value, that means that a higher threshold is better, because data is going to be processed faster, okay? And you're going to get exactly, it's going to be more clean, even getting the same amount of images. So see, this is what I meant, that this value here, those 300 that are missing, are probably things that are indexed and that it didn't read correctly. That's a bug in the script. However, the script that is used for full indexing doesn't have that bug.
Or you would just finish when all the data was indexed.
Exactly. Okay. And see, now it's higher. See? Now it has a higher percentage. You see? 57.9 versus 57.6.
Oh yeah.
Okay. Johnny, do you have time? Should we sit down and take a look at the results and so on? Do you want to go to the office? Do you want to stay here?
Okay.
Whatever you want. So you have them here, we can take a look. If not, we can go to the cafe. Okay. So, okay, then continue like this and let's see how, so what the data looks like. So